Welcome to this video where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in this video we are going to talk about content contained in chapter 13 and talk about output regulation. The setup we discuss here is shown in the block diagram on the left, where we have a plant for which we want to design a controller based on output measurements and taking a reference signal into account, meaning we design our controller based on the mismatch between the reference signal and the measured output. And we start with the dynamics shown here on the right, linear dynamics depending on the state, input U, and disturbance D, and similarly the output Y depends on the state, the input, and the disturbance. And here the goal is to achieve asymptotic reference tracking, meaning we want to achieve that y of t is converging asymptotically to yr, and that should work regardless of the disturbance signal d here. So let's get started to solve that problem through reference tracking, and to get there we first need a bit of notation. So first we define our error signal here as the mismatch between the output and the reference signal, which then allows us to rewrite that slightly using the output equation here on the right. In output regulation we will rely on the following assumption, meaning our reference signal can be written as a linear system of the form here, so expressed through a matrix AR, and we also assume that our disturbance follows a dynamical system, a linear dynamical system of the form shown here. Combining all of this information into new variables and then a new representation of our dynamical system. So first we combine reference signal and disturbance in the so-called exosystem, which then can be written in terms of the linear system W dot is equal to A1 times W. And then using this information in our system dynamics gives us the corresponding dynamical system in terms of X dot, W dot, and the measured and the output mismatch E in terms of the error dynamics E here. And just to give then a motivating example how corresponding results might look like. So we might be after tracking a piecewise constant reference signal. So as shown up here, piecewise constant reference signal changing after 10 seconds with its reference value. We might have a disturbance signal with a particular frequency, here shown on the right, where we also show that the disturbance can change after a certain time. So here the frequency changes after 20 seconds. And as mentioned before, we want to achieve asymptotic reference tracking. So we see here the convergence of x1, in this case, which is our output y, to the reference signal. And we see this transient performance happening whenever we either change the reference signal or when the disturbance changes. We're only interested in the output. So here we started with a two-dimensional system. That means that the second component x2 might not necessarily converge to a constant value or to zero. Only the output converges. And here we have additionally shown the convergence of the difference between y and yr. Okay, but with that, let's get back to our output regulation problem, which we have written in terms of the dynamical system here. And for this system, now we want to define a controller depending on x and on w such that the error goes to 0, and in the case that w is equal to 0, meaning that the disturbance is equal to 0 and that the reference signal is equal to 0, we also want internal asymptotic stability, meaning that the whole state x is converging to 0. To achieve that, as defined up here, we use a controller of this form, and if we plug that in to our system up here, then we end up with these closed loop dynamics down here, where we can define a new matrix now AC and BC, simply depending on the controller gain Kx and the controller gain Kw. And if we then translate the conditions here in terms of error convergence and state convergence in the case that the disturbances are 0, then that means that our task here is to find the Kx and Kw such that this new closed loop matrix AC is a Hurwitz matrix, and such that the limit here of these error dynamics is equal to 0, meaning CXC plus DCWT should go to 0 for t going to infinity. And the corresponding result that can be established here is written here as follows. So if we assume that AC is Hurwitz, and if we assume that that matrix A1, which here is defining our exosystem, so depending on the disturbance dynamics and the reference dynamics, if we assume that this matrix has no eigenvalues with negative real parts, then the following statement holds, namely that the error is going to 0 if and only if there exists a matrix XC solving these two matrix equations down here. So that is the result we rely on, and if we translate that to now the controller design, then that means that we can select under appropriate conditions on the matrix pair AB a controller gain Kx such that A plus BKX is Hurwitz, meaning we satisfy the condition here on AC being Hurwitz. And then we can solve this linear matrix equations here in the unknowns XC and KW to find XC and KW, which then defines the overall controller. So that's nice. That's giving us a clean solution in terms of solvability of the output regulation problem. But what is potentially problematic here is that we have to design, in this case, Kx and Kw sequentially. So if we first design Kx, and then as a second step, we would design Kw. A way to avoid that is by considering a coordinate transformation, namely to introduce this new set of variables x and u together with the corresponding coordinate transformation written here, and then consider the so-called regulator equations now in the unknowns x and u. And now if we are able to solve these regulator equations and find x and u, then as a solution we get that for all kx we get an explicit expression for kw, meaning we essentially only have to do this construction once, and we get for a given kx immediately a kw, and can tweak kx and kw simultaneously. The corresponding results justifying that is that here now again the regulator equations are solvable for any E and F matrices defining our linear system. Now in this case if and only if the eigenvalues of the matrix A1 here are such that the rank of this matrix is full, meaning the rank of this matrix is n plus p. So this provides a solution of the linear output regulation problem. This can also be extended to the setting of uncertain linear systems, meaning where the matrix matrices A, B, E, C, D, and F depend on a parameter delta, and then corresponding results can be derived. Or one can also consider a nonlinear output regulation problem and derive corresponding results, starting with the same structure in terms of dynamics x dot and in terms of dynamics w dot, and a corresponding output equation representing the error, and then derive corresponding solutions, a corresponding solution for this output regulation problem. And that already concludes the topic, the snippet I want to discuss with respect to output regulation, and you find more detailed information in the chapter. And then in the next video, I'm going to continue with optimal control.